So let's spend some time today talking about your project because generally speaking, you guys seem to not have it done. So this is what my schematic looks like. These are the numbers that I got there, an estimation of what you should get from your calculations. Things are off by the order of a couple of ohms and all that kind of good stuff. But generally speaking, this is what your schematic should look like. And I have one pulled up in LT Spice as well. And if we simulate this, what we get, let me make sure this is the right one. This is not the right one. This guy on the left. Okay. This should match pretty much exactly what you get in LT Spice. Okay, no problem there. I don't know why some of you guys did the schematic version in electric and then it was giving you gains of like -5. I honestly don't understand that, so I'd be happy to look at things again. If I go back to my schematic here real quick, this literally should not matter at all, but all of these resistors are high-res poly resistors, and all of these capacitors are listed as poly 1 to poly 2 capacitors. This MOSFET here in the middle is, let me go to my components library, right? So if you mouse over capacitors, you have normal, electrolytic, or poly 1, poly 2. It should not matter, but because this is supposed to be a poly 1, poly 2 capacitor, I put it in as that. Similarly, I'm going to have to delete that or it's going to freak out. If you mouse over the resistors, you have normal, so like a regular LT Spice resistor or an N poly, etc. I made all of mine high-res poly because that's what these are supposed to represent. That should not matter, okay? For the MOSFET, you have multiple options here. The one that I chose is just this general one right here where it doesn't have a body connection because we don't really particularly care about it right now. One thing that is maybe less than obvious to you all is in the problem statement, it made mention of a scaling factor of 300 nanometers. So electric does not deal in absolute lengths for literally anything. Everything is done in multiples of a scaling factor, okay? So if you want to get a 15 micron wide transistor, you say 15 microns divided by the scaling factor of 0.3 microns is 50 scaling factors, which is why my width is 50 scaling factors. Similarly, 1 micron divided by 0.3 microns is 3.333 scaling factors, which is why my length is 3.333 scaling factors. Something that, so one issue that I've seen happen last quarter and this quarter is sometimes when you run your LT Spice thing, or you write your spice deck and all that kind of stuff and try to run your simulation, sometimes it freaks out and says, I can't find the model for N or something like that. So when you place a transistor down and you have your cursor, like if the transistor is in the white box, that means it's the thing that's currently selected. If you go to Tools, and then you go to Simulation Spice, you can literally click a button here that says Set Spice Model, and it will pull up. So let me delete this guy, and I'll show you exactly what I'm talking about. So I'm going to drop a transistor down in here. And click on this. Tools, Set Spice Model, and it just puts a text label here. If I mouse over the transistor itself and then I control left click, it cycles through all the different things that are clickable. And I just want that text to have a white X over it. I press Control I, and I'm literally going to type NMOS, which lets SPICE know that this is treated as an NMOS, a generic NMOS transistor. And I'm going to move this text out of the way because it puts it in a dumb and inconvenient spot. And then let me wire these guys back up. Node to node. Node to node. And 50 over 3.333. Apply. Okay. And just for the hell of it, DRC, no errors. Write my SPICE stack. B out over B in. Apparently I have caps lock on. And I got the plot that I'm supposed to be looking for. So again, I'm not really sure why some of your even schematic representations are not giving you the gain that you want them to. So I'd be happy to look at things to help you sort that out. With regards, let me close this out. With regards to the layout, here's what mine looks like. Where I did take the time this morning to draw out each individual resistor and all that kind of good stuff. So this guy over here in the top left-hand corner is a 7.1K resistor. So each of these blocks of 5 is a 1 kilo ohm resistor wired into the next. Each of them represents a 200 ohm chunk. So they're all just the standard 40 by 10 high-res polysilicon thing. To get 0.1, I just put 2 of them in parallel, right? 2.5K, a similar thing. 2.8K, a similar thing. For this 270. I have 1 in series with 3 in parallel, which is really 266.7, but that's close enough to 270 for me. You could play around with widths and lengths and all that kind of junk if you wanted to, but I did it in the laziest way possible, just using effectively a 200 ohm resistance unit cell and then wiring them up together to get what I wanted. The capacitors that I've laid out are done exactly as you're told to do in the little practice thing for doing an RC circuit. One thing that I think I might be doing slightly different than some of you is the way that I do my exporting things. So let me just zoom in here and just pick this point right here. Anytime you have one of these white dots highlighted, if you press Control E, that allows you to export that node as something to LT Spice, which is how I got V out here, VG, VS, and VD, and all that kind of stuff. For this particular layout, you absolutely have to export a drain terminal, a source terminal, and a gate terminal, because that's how you're telling LT Spice to interpret these capacitors is between. So I'm saying I have an output capacitance between node VD and node V out that has a value of 50 nanofarads. That's the syntax here. So if I forget to export VD or V out, it just says that node's 0 and nothing works right. So you have to make sure that every node you reference in your capacitor statements is actually exported, or your circuit won't work correctly. So yeah, like another thing real quick here, my transistor here isn't 50 over 3 1/3 because in your layout, you need to use integer numbers for integer multiples of your scale factor. So 2 possible options would be to make it a 45 over 3 or a 60 over 4. Both of these are going to be close to 15 microns over 1 micron. Race.
Can you explain what you mean by capacitor statements?
Sure. So let me zoom in here. So because electric does have built-in capacitors, but you were asked specifically not to use the built-in capacitors. So all of these capacitors were laid out using a section of pure. So if we go into the components menu, and up here on the top left, if we put pure, we can choose polysilicon 1 node, polysilicon 2 node, and various other materials. So each of these was laid out using a chunk of polysilicon 1, a chunk of polysilicon 2, to which I attached electrodes using the poly 1 to metal 1 contact and the poly 2 to metal 1 contact, which is up here. Okay. Because you are making an element out of pure things that do not have wire representations inside of electric, you have to set LT Spice up to be able to interpret what that is. So this statement right here is a spice command. And you can access giving spice commands by going into miscellaneous and then tell it spice code. So the syntax for these capacitors is the name of the capacitor. I arbitrarily chose this as C out so that it would match the LT Spice thing that you were given. The capacitor is connected between node VD, which is the drain node for the transistor, node V out, which is the output node for the circuit, and it has a value of 50 nanofarads. The reason why we're doing it like this actually is because in the assignment sheet, you were told that the capacitance per unit area between poly 1 and poly 2 was 200 picofarads per micron squared. For a real C5 process, it's about 850 femtofarads per micron squared, which means your capacitors would be on the size of like a millimeter by a millimeter. They'd be huge. It is what it is, but you know, like your capacitor would take up effectively your whole damn screen for every capacitor that you were designing. So we chose to force the capacitor to behave that way with a heightened poly 1 to poly 2 capacitance by doing it this way.
So you're linking it to the circuit by labeling the VD out.
So those are the two nodes. Yeah, so that's the positive polarity terminal is VD, the negative polarity terminal is V out.
And the capacitance between those is
Labeled C out and has a value of 50 nanofarads. So if we scroll down here to my 10 nanofarad, it's the capacitor connected to the source terminal, which is why I very unimaginatively labeled it CS. It's connected between the source node and ground, which is 0, or I could put lowercase GND there. It wouldn't make any difference whether I choose 0 or that. And it has a value of 10 nanofarads. And then the one at my input is between my input voltage node, so that's where VN is applied, and the gate node that has a value of 100 nanofarads. This is the syntax that's literally described to you in the handout for simulating an RC circuit in electric. That's uploaded to Moodle, right? Yeah. This 2.8 kilo ohm thing here, that's literally just a text reminder to remind me, because I had all of the resistors built on one side, all of the capacitors built on the other, so I just put annotation text here. So this 2.8K does absolutely nothing. You can annotate things by going into the miscellaneous button and then just putting annotation text, and it just opens a text window where you can put text all over the place. So for complicated circuits like the ones that I have people design for ELEN 438, I typically get in the habit of labeling like the drain, source, and gate for every transistor, and I call it like D4. Or if I have a bunch of transistors in parallel forming a single transistor, it's D4A, D4B, etc., so that I can keep track of what everything is, because as you can imagine, things get pretty gnarly in this when you have tons of transistors all over the place and you're trying to figure out where the hell is this thing actually connected to again. So labels are good. So anywho, this is what my particular layout looks like. Yours can look wildly different. It just depends on where you put things. Race.
So those transistor terminal exports, those are also going to be in the schematic?
They don't have to be. So the reason why they don't have to be in the schematic is because we're using a predetermined capacitor in the schematic representation, and we are creating our own here. There's nothing stopping you from doing that. So all it means when you export these things is that that's something that you can look at in LT Spice. Because I'm defining this capacitor to be placed between node VD and node Vout, if I don't export them here, it doesn't know where to put the capacitor. Okay, or it doesn't know to interpret this thing as a capacitor between these nodes having this particular value, I guess would be a better way to put it.
And then do we need to be concerned about a P-well around the transistor at all? Or-
Not particularly, because if we zoom in a whole hell of a lot, there is a built-in P-well around it. And because electric by default uses a substrate of P-well, everything is P-well unless you tell it otherwise. So you don't really need to do that. The only thing I would really worry about hooking up a P-well for would be to do a guard ring around the body terminal, and we're not even bothering to do that here. So yeah, and that sentence I'm sure means nothing to all of you. So yeah. The exact same thing as the other one, Andrew.
And is that VG label, is that the same like click white node and you export it?
Exactly right. All of the things that are associated with a node here are exports. So VG, let me zoom out here. VG is an export. VD is an export. VS is an export. Vout is an export. Ground is an export. VDD up here is an export. So I'm just telling it, these are the nodes that I have in my circuit. I'm telling LT Spice, these are the nodes that I have. These statements right here tell me between what nodes the capacitors are placed. And then the Spice code at the top middle this is saying I have an element called VDD placed between node VDD and ground that has a voltage of 3.3 volts. This statement here, right, it's working, but I think actually you could do VDD or VDC here to tell it it's just a DC source, I think. This one says I have a AC voltage source placed between node VN and ground. Or no, that's the name. Yeah, so that's the name, VN, between VN and ground, it's an AC source and it has an amplitude of 10 millivolts. So I guess here, because I didn't tell it something specific, it just interprets it as DC because that's the default whenever you put a voltage source in. This statement right here is to tell it to do an AC sweep. So the AC analysis, decade sweep, 100 points per decade, starting at a frequency of 1 kilohertz, ending at a frequency of 1 gigahertz. This guy right here is actually probably one of the most important statements. So it says, treat NMOS as the default NMOS model, but change all of these parameters to this specific thing so that we can set mu n Cox 200 times 10 to the minus 6 or 200 microamps per volt, set lambda equal to 0, set our threshold voltage equal to half a volt, the width to 15 microns and the length to 1 micron. If you don't put these things in here, it just uses whatever LT Spice says how an NMOS behaves, which could be good, could be bad, probably going to be bad. One of the things that I dislike the most about LT Spice is that there's not a way to do this for BJTs. There's a way to approximate it so you can set your beta values, by saying, treat all my BJTs as a particular type of BJT and then change the beta value to this. But you can't, or at least I haven't figured out how to change the saturation current parameter, IS, for the built-in models. So that's why it's annoying to me, because otherwise we could simulate all of our circuits in this class, and I'm sure you guys would want to beat me to death in the street. So I'm going to just simulate this guy too, just to show you what it's supposed to look like here. And so it looks very, very similar to what we had for the schematic, except that there's some stuff going on here at the high frequencies. And the reason for that is all of these parasitic capacitances that are lined up here, right? So this is why it rolls off at around 20 megahertz. Whereas for the the schematic version, which doesn't take into effect parasitics, continues going. So I had it set up, maybe I still do, as a side-by-side comparison of the two things, right? Where the scale factor on both sides is the same so that we can really see what the difference is between the layout version and the schematic version. And they are effectively identical. We can see here, my gain is actually a little bit above 7 dB, and in the midband here, it's at straight on 7 dB, but everything else is pretty much the same. So frequency response is the same, phase response is the same until we get somewhere in the ballpark of 20 to 30 megahertz, and then this guy falls off considerably due to all of those parasitic capacitances. Just for beating things just straight to death, I also where is Dropbox? There we go. Made a version of the circuit containing just the MOSFET high frequency capacitances, where I just gave them some kind of generic values. And if I simulate this, that is not a division sign. That would have probably done something wackadoo. The left, and I've expanded out the frequency, right? So instead of starting at 1 kilohertz and ending at 1 gigahertz, I had to go all the way out into the terahertz range for us to see the actual high frequency roll off here with just those capacitors. So the parasitic capacitors that are introduced by every single little chunk of that high res poly forms a parasitic capacitance with the substrate, because it's a layer of polysilicons on top of the substrate. Every one of those has a parasitic capacitance. There's a bottom plate capacitance formed between the bottom plate of your poly 1 to poly 2 capacitors and the substrate that are parasitic capacitance that are messing with things. And what that's doing is that's pushing that high frequency roll off further and further back. The more parasitic capacitances we add, the shorter the bandwidth of our system is. So anyway, all right, so I guess the question now is, what do you want to do for today? I obviously have a binder full of notes. We could talk about the MOSFET high frequency model stuff, or we can spend the remainder of class me helping you guys figure out your project related crap. What do you want to do? Which of those two options, Bailey?
Door number 2.
Yeah, door number 2.
All right, so we're gonna spend the rest of the class then talking about your project stuff. I'm just gonna sit up here and help. I'd like to give you guys an extension on the project until Sunday evening, just in case things aren't cleared up. Does that sound unreasonable? All right.